Welcome to the second session on Aspen Plus, where we'll be looking at the simulation environment and hopefully run our first simulation. So previously we looked at the model palette, some of the features of the model palette, and the many unit operations modeled in Aspen software. So the models fall in categories. We have the shortcut models. So usually they just require some input and they give you an output, but they require you do not need to know much detail about the inner workings of the equipment or the model in order to use this equipment. So, an example will be for distillation. There is a shortcut method where you specify the minimum or the barest of specifications. You basically have a problem, and the model is able to give you a good estimation of what a capable equipment might, the specifications of a capable equipment might be. And on the other hand, we have the detailed models. They In that case, you need to know a lot about the equipment being, well, the process being modeled, and they also tend to perform more rigorous calculations or computations, right? So we'll see a lot of that as we move on. So to define a flow sheet, you need the blocks, you need the streams. Then you can also model this, modify this, right? You can name blocks and streams, you can change connections, you can add new pathways and so on. So that takes us to our first problem, and we are going to monitor the flow of all we've learned so far, specifying components, property methods, and we'll see how this ends up in solving all of these come together to solve a specific problem. So I'll quickly switch to Aspen Plus. So we have a problem here. Ammonia is produced by reacting nitrogen gas with hydrogen in some ratio. Since nitrogen is obtained from air composition, argon composition, the reaction occurs at 200 bar and 400 degrees Celsius. Our supplies are able to deliver at the right pressure, but not temperature due to the cause of it. So we are going to model this problem in Aspen. And the first thing to do is we have to identify our components. So there's ammonia, there's nitrogen, there's hydrogen, and there's argon. So I have most of them entered here, but you can pause the video and make sure you have all the components in there. So next I'm going to specify my property method. So it says if you don't know, then Penn Robinson. Right, so we are going to use the Penn Robinson property method. And this should do it. Then quickly, the simulation environment. So let's look at the blocks we would need for this. We have a reaction, so we need a reactor. We have some heating required, so we need a heater. We have to cool somewhere here. We need a cooler and then a separator. And since we'll be doing some recycling, we'll need splitters and mixers. Right. So that's a summary of all the equipment required to solve this problem. So you've added our components, we specify the property method. So let's add the blocks. So the first things we need are heaters. It's a nitrogen heater and hydrogen heater. Right. Or at this point, I have my unit operations or my flow sheet almost set. I have the blocks. So without the recycle part, right? So the next step would be to connect my streams. So I come here and I click on material, and that activates all the stream, the points, connection points. So I can add a stream here, a stream to feed the equipment. I can also connect my equipment, my blocks, streams. So taking note of what each the requirement for every equipment, whether it's a single input, single output. In the case of a mixer, double input or more, single output. So, so here I could delete a stream if I wanted by just clicking on the hitting on the delete button on my keyboard. I could delete that stream. And I could also rename the stream, call it paper, maybe. I could change the position of blocks. Right. So I'll take a time and play around some of these, and you can pause the video and connect all your streams and label them appropriately, or as you deem fit. So beyond this, we can now go on to specify our material streams. So the way you do that is by double clicking on that stream, right? And that should take you to the stream specification page, where you'll be asked to specify the conditions for that stream. So we go back and read the parameters from our problem. And we had 100 kilomoles of nitrogen being fed per hour. And then the temperature, we saw at it was a room temperature. So here we take in temperature as 25 degrees Celsius. It was already being fed at 200 bar. So take we specify the composition of that stream. It's just nitrogen. More fraction is one. And that should be it for the nitrogen stream. So you can pause the video and do the same thing for the hydrogen stream. So you should have this, and that should be it for material streams. Remember, Aspen is a forward only calculator. It does not perform backward calculations, meaning you only specify feed streams and it does the rest of the calculations for the product. It determines the product or the output, not the other way around. So the next thing would be to specify blocks or equipment. So you do that by clicking on the specific equipment. So for a heater, we want to specify the outlet temperature of the product. So we are heating from 25 to 400 degrees Celsius. I specify that there should be no pressure drop, so maintain at 200 bar. And that should be it for the heater. The same thing can be done for the other heater. And the blue check mark shows that the specifications are fine or enough. Our mixer is also operating at the same pressure. The outlet temperature is the same. And the reactor. Reactions okay. Same conditions. So we specify the operating conditions, and then we now have to add our reaction to the reactor. So a reaction is a nitrogen plus hydrogen producing ammonia. Quick check. Nitrogen stream had 0.5 more percent ammonia, so make that correction if you didn't. Argon, sorry. Right. So you have the balanced stoichiometric reaction. If it's a reactant, you negate the coefficient. If the product stays positive. Fractional conversion. Problems at 33% conversion of the limiting reagent, in this case nitrogen. 0.33. That should do. That should be all for the reactor. Next, we move to our cooler. And we're going to determine the outlet. We're not provided an outlet temperature in the problem. So we're going to determine the best iteratively what that outlet temperature should be. Say still at 200 bar. And the last should be the flash. We should have the same conditions. After this, we should be able to run the simulation. So you can come up here and click run. We can go to next. So you'll be prompted until that all the inputs required is complete. So we can run the simulation then. So we have our results available. You can see that on there. So generally there are ways, many ways to view different results. Some of the most interesting ones can be the block results. So here you right click on the equipment and go to results. There you can see the outlet temperature and pressure of the reactor, the heat duty. And it indicates our reaction was exothermic. And this is the heat duty, the amount of heat we had to remove to keep the temperature constant. You can also see the streams attached to that equipment, again by right clicking on the equipment and selecting the stream results. And that should take us to all the connected streams. So the temperature, the inlet and the outlet. So we have all that, molar flows. And you can see the flow rate of all the equipment, the components. Sorry. Another thing we could do is we could come to the stream summary, clicking on the home tab. If you click on stream summary, you can see it'll give you a summary of all the streams in the flow sheet. We could also generate a report for the blocks, that will give you a notepad for so mass and energy, overall mass and energy balance, and all that. So find the flow sheet. You can see similarly for the flash. So here you'll be interested in the separation results. So see how much of need I need a full stream. Right. And see the temperature of our product is 400 to 40. And it comes to the mole flows, ammonia, and see how much separation you get based on the feed stream. It's not been able to recover a lot of ammonia in the liquid phase. So we might need to drop the temperature further to do that. So that should bring us to the end of this session, Aspen Plus. Hopefully At the end of this introductory session, we've been able to cover what it takes to start a flow sheet to solve a problem using Aspen Plus. At least this should give a beginner a fair idea of the general flow of or the general syntax of the software. And so looking onward, we're looking at specific equipment, distillation columns, the heat exchangers in our next or upcoming videos. Right. And this material, the links to this material will be provided in the description for anyone who wants further explanations for the reasons why some of the things were done or more exercises. Thank you.